Today's objective is to learn decomposition of a rational function into summation of partial fractions. In the original rational function, its denominator has 1, 2, 3 distinct irreducible factors. Each one of them will introduce a term in the decomposition. This one. Notice that x plus 1 has a power of 2. That will introduce two terms, x plus 1 and x plus 1 power 2. In the decomposition, if the denominator is a linear factor, then you have a constant term ABC in the numerator. Notice that we talk about the linear or quadratic is to the irreducible factor here. So, for example, although x plus 1 power 2 is a quadratic, but its irreducible factor is just x plus 1. So in that case, we'll still have a constant term in the numerator. Well, for x plus 1 here, it's a irreducible factor, is a quadratic. That's why we need to use a linear function on the numerator with two coefficients, d and e. Later, you will learn in the calculus that it's often very difficult to directly integrate or take derivative of a rational function like this. And it's much easier to apply integration or derivative to simpler partial fractions just like this. One big reason that we want to learn the partial fraction decomposition is to be able to simplify a lot of those calculations. This page summarizes the steps for partial fractions decomposition. Start with the rational function represented as division of a polynomial n divided by polynomial d. The first step would be applying non-division. So you will have a polynomial, the quotient, plus its remainder n1. The degree of the remainder n1 is less than degree of the divisor d of x. The partial fraction decomposition we learn here will only be applied to this n1 divided by d. That is called the proper rational expression because the degree of n1 is less than the degree of d. Step 2 is the factorization of the denominator of the original rational function into factored forms. For every irreducible linear factor or irreducible quadratic factor, you will have its multiplicity of m. The m could be equal to 1. Step 3, you want to write down all the linear factors. For each factor, linear factor of this form, the partial fraction decomposition must include all the following sum of these fractions from the power of 1 all the way to power of m. Each one of them will have a constant coefficients in the numerator. And step 4 will be writing down the terms for the quadratic factors. For each factor of this form, the n could be 1 or greater than 1. The partial fraction decomposition must include all the following sum of n fractions. And numerator must be a linear function with the coefficients to be determined. And notice that you will have 2 times of the number of coefficients to deal with. If m equals n, in the case of quadratic versus the linear factors. Now let's take a look at the example. Step 1, you want to completely factorize the denominator. That will be x minus 2 times x minus 3. Step 2, you want to write all the linear irreducible factors. Each one of them will introduce a term. In this case, we have x minus 2 and x minus 3, with a and b are coefficients to be determined. Step 3 is to find a and b to satisfy equation 2. To do that, we add a over x minus 2 plus b over x minus 3, that will equal to, you make the common denominator, then you're adding a times x minus 3 plus the same common denominator, b times x minus 2. You add them together, you will have x minus 3. Then you add in the denominator here, adding the numerator here, you will end up with a plus b, x plus minus 3a minus 2b. And the equation in step 2 says this must equal to 1 over x minus 2 times x minus 3. Then we must have, in order for this to be true, we must have a plus b, x plus minus 3a minus 2b must equal to 1 for the numerator. Notice that we are claiming that this rational function and this rational function, they must be the same function. That means their numerator must be equal all the time for all the x. To make that happen, the only solution is to make a plus b equals 0 and the minus 3a minus 2b equals 1. And solve this linear equation, you will have a equals minus 1, b equals 1. And this indicates that the original rational function 1 over x is 2, x minus 3 can be decomposed into summation of x minus 2 minus 1 plus x minus 3 to 1. And you should be able to verify that this decomposition is correct. And this is how we solve a linear function for a and b to be able to finish the decomposition of the partial fractions. Let's look at the second example here. In this case, the denominator has a linear factor x and x plus 1, and the x plus 1 has the power of 2. That means we should be able to decompose this rational function into summation of the following. A over x plus b over x plus 1 plus c over x plus 1 squared. We must include the factor x plus 1 because the x plus 1 linear factor has a power of 2. So we must include all the lower power of this linear factor up to power of 2. Now we need to find the coefficients a, b, c, such that this decomposition, the summation of the decomposition would be equal to the original rational function. That is 2x squared plus 20x plus 6 over x plus 1 squared. Again, we must make a common denominator to be able to sum up the terms on the left-hand side. That is x, that's x plus 1 squared. You make a x plus 1 squared. For the second term, you will make the common denominator. Then you multiply b by x times x plus 1. And for the third term, will be c times x divided by x plus 1 squared. Now you can sum them up. You will get, there's a missing x here. X plus 1 squared, a x plus 1 squared plus b x plus 1 plus c of x. This equals, after some simplification, a plus b x squared plus 2a plus b plus c of x plus a divided by x plus 1 squared. And this must equal to the original rational function, that is 5x squared plus 20x plus 6 divided by x plus 1 squared. Now we can compare the coefficients of the numerator. We conclude that a plus b must be 5, and 2a plus b plus c must be 20, and a must be 6. If we can find a, b, c to satisfy those conditions, then we can be sure that the original partial functions will be the same as your decomposition. The same as the last example, we arrived at this linear equations for ABC, that is a plus b must be 5, and 2a plus b plus c must be 20, and a must be 6. You solve this equation, you will get a equals 6, then b equals minus 1, and c must be 9. You conclude that the decomposition will be written as 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared. If you want to verify that this decomposition is correct, you would like to add them up, right? So you find this common denominator to sum them up. That is, the common denominator is x times x plus 1 squared. They would have 6 here, x plus 1 squared minus x times x plus 1, then plus 9x. Essentially, you are reversing every step you just did. We can verify if that will give us the original rational function. We'll do some simplification here. You have 6x squared here, then you have 1 minus x squared here, then you will have 5x squared. You have 12 x from the first term, then minus x, then plus 9x. You have 20x. The constant term would be 6. indeed, you go back to the original rational function. So that tells us your decomposition here is correct. Let's work on the third example here. In this case, we would want to decompose this rational function into two terms: a over x plus 1 plus b over x squared plus 4. Since the second term, you have a quadratic in the denominator as an irreducible factor. So we must include the linear function as its numerator here. So that will be bx plus c. Now we have a, b, and c, three unknown coefficients to be determined. Now we play the same game as before. We would like to sum this decomposition back. We'll have the common denominator formula here. There will be a times x squared plus 4 plus x squared plus 4 times x plus 1 bx plus c times x plus 1. Now we want to simplify it a little bit. The numerator, the denominator will be just copied down. The numerator, let's collect the coefficients for x squared. You would have a plus b as the coefficients for x squared. Then let's look at the coefficient for x. You would only have that from this term. That will be b plus c. Finally, you have the constant term. That will be plus 4a plus c. So after you check everything is correct, then the expectation is that you add up the decomposition. That result would be exactly the same as the original rational function. So that means we must have a plus b equals 7, because that's the coefficients for the quadratic term in the numerator. B plus c is 5. That's the coefficient for the linear term in the numerator. And finally, you will have 4a plus c equals 23. 4a plus c equals 23. You want to solve this linear equation for a, b, and c. How to solve this? Let's mark the equation is 1, 2, 3. Then 1 minus 2, you will get a minus c equals 2. Then you copy equation 3, is 4a plus c equals 23. Now you add these two together, you will have 5a equals 25. That immediately gives you a equals 5. Then c equals 3, and b equals 2. This way we get ABC. Now we use ABC in the decomposition. You will have this decomposition be 5 over x plus 1 plus 2x plus 3 over x squared plus 4. Of course, you would be able to repeat this process, but add them up, and to verify that this decomposition is correct. And this example is slightly different because the degree of the numerator is actually greater than the degree of the denominator. So your first step would be do the non-division to get this remainder. And this is how we do the non-division. We have 4x cubed. Since we are missing the quadratic term, we'll just leave a space here. Minus x plus 2. Divided by 4x squared plus 4x plus 1. I will put 1x here. That will give us 4x cubed plus 4x squared plus x. Right? Then you do the subtraction. You would end up with minus 4x squared minus 2x. Then you move this 2 down here, plus 2. Next, I will put minus 1 here. We get minus 4x squared minus 4x minus 1. Subtract again. You would have 2x plus 3. Right, the non-division gives us the first step, that is the original rational function can be written as x minus 1 plus 2x plus 3 divided by 4x squared plus 4x plus 1. From the previous class, this is how we expose this linear equation for the slant asymptote. Next, we are going to decompose this term into partial fractions, because now this term has the degree of the numerator that is smaller than the degree of the denominator. To do that, we must first factorize the denominator, and that is 2x plus 3 over 2x plus 1 squared. That is a factorized form. Play the same game as before. We would like to decompose this rational function as a summation of a divided by 2x plus 1 plus b divided by 2x plus 1 squared. Notice that although we have a quadratic term here, but since the irreducible factor is still linear, right? Then we would only have a constant coefficients in the numerator. And because this irreducible factor has a power 2, then we need to include its first power term as well. So we will play the same game as before. That means we are going to sum them up using the common denominator. That will be 2x plus 1 squared a times 2x plus 1 plus b. Simplify. You would have 2a of x plus a plus b. Then you would compare the coefficients for x with the original rational function, which is here. And you will compare 3, that should equal to a plus b here. It will form the linear equation for A and B, that is 2A equals 2 and A plus B equals 3. And this gives A equals 1 and B equals 2. Now you finish the decomposition for this term. If you put all things together, you will get the final decomposition of the original rational function will be following. 4x cubed minus x plus 2 divided by 4x squared plus 4x plus 1 equals x minus 1. So this is gotten from the non-division slant asymptote. Slant asymptote. Now for the remainder part, you have the decomposition of the partial fractions with A and B, which is written as 2x plus 1, because A equals 1, plus 2 over 2x plus 1 squared. This is the final decomposition. For the last example, we would first factorize the denominator into x minus 1 squared plus 4. We just copy the numerator. For this one, we would like to decompose the partial fractions as the following. Because your factor of x coefficients A plus the linear factor x minus 1 coefficients of B, then you have the quadratic factor. Then because x squared plus 4 is the irreducible factor, that means you need to introduce a linear term in the numerator. That will be cx plus d. Now the following task will be to find A, B, C, and D to make this decomposition work. To do that, we simply just add this decomposition back to see what happens, right? Yeah, you have to have, again, make the common denominator to be able to add everything back. When you do that, you will have A is multiplied by x minus 1 squared plus 4 plus B times x squared plus 4, then plus cx plus d O times x minus 1. Now let's simplify the numerator. We simply copy down the denominator. Now on the numerator, we want to connect the coefficients for each term of the polynomial. Let's first look at the cubic term. We would have A, right, from this product. Then you will have B here. Then you would have C here. So that gives us A plus B plus C times x cubed. Then next look at the quadratic term. You will have one quadratic here. That is minus A. You don't have any quadratic term contribution from this, you will have 2 quadratic from here. That is d times x squared, then minus c. You have minus a, minus c, plus d here. Now let's connect the coefficients for x term. That will be 4a from here, then plus 4b. Finally, you have minus d for x. To do this, you search, each one of the multiplications to look for the terms you would like to connect here. Finally, the only constant term will be 4a. It's a minus 4a. Now we can compare the coefficients we just had with the coefficients of the original rational functions numerator. We would have a plus b plus c minus a minus b would equal 0 because there's no quadratic term in the original numerator. 4a would equal minus 4 here, and minus 4a would equal minus a. Now we are going to solve this system of linear equations for a, b, and c. We have a equals 2. We're plugging a equals 2 into the equation. You would have b plus c equals 0, and minus c plus d would equal 2, and the 4b minus d equals minus 12. It's 4b minus d equals minus 12. Now we add these two together. You would have b plus d equals 2. Together with 4b minus d equals minus 12, you would have 5b equals minus 10. That means b equals minus 2, and d equals 4. The final solution would be a equals 2, b equals minus 2, c equals 2, and d equals 4. And the final partial fraction decomposition would be 2 over x plus minus 2 over x minus 1 plus 2x plus 4 over x squared plus 4. This will be the final answer.